All right, so now we arrive at learning how to solve those rational inequalities again. Okay, so the idea we're about getting into here is not necessarily related to the vertical asymptotes of a rational function or horizontal asymptotes of a rational function. So it is not that important to learn this detail after you have already known about vertical asymptotes or horizontal asymptotes. As long as you have already seen and be aware about what a rational function is, as well as the domain of a rational function, we should be able to carry that our understanding into learning about rational inequalities. Okay, so again, this idea we're about to learn is not necessarily related to vertical asymptotes or the horizontal asymptotes. So it's not that required that you got to know vertical asymptotes or horizontal asymptotes. However, it is strictly required that you have learned from my lecture about the polynomial inequalities. Because once you have learned about the polynomial inequality or how to solve the polynomial inequalities, the majority of those ideas will be carried over and used here when we're solving rational inequalities. So along with what I said there, then it is extremely important that, it is required that you view this lesson, learn this lesson after you have learned about how to solve a polynomial inequality. Okay, and so other than that, let's get started. All right. And so now I am going to erase the title of the discussion topic here so that we can maximize the board space here. All right, so now that we're looking at, let's look at the following inequality right here. And I am going over the simpler kind of problem where all terms are being brought into one side and successfully put into one rational function. So, and you will see what I mean when I start bringing it up. Okay, so let's look at the following. How about x minus 2 in parentheses times x plus 1 and then the x minus 1 in the denominator times x plus 1 in the denominator. Okay, so this is just a demonstration problem right here. And so what we have here is a rational the function. And then we want to solve. So I'm demonstrating the idea right here. We want to solve this inequality to be less than 0. Okay, I want to solve this inequality. We have whatever that is being less than 0. We want to solve that for x, of course, so because the main variable here is x. All right, we solve that inequality for x. And so observation is telling us, so now I'm being a demo problem right here, allow me to bring in as much details because there are a lot of logical understandings as well as how the ideas we've learned about polynomials will be carried in here. So allow me to move on at somewhere a relatively slow pace right here for you to really catch all of that, all of those logical understandings. So as far as observation, I see this inequality came out as, now see, good thing is one side is already a 0. And so all we have to do is we want this expression here as a rational expression to be less than 0 in this case. It's an inequality. Okay, and so, and as I said earlier, we are going to just simply focus on those problems, on those simpler problems where we already have successfully brought all terms into one side, like this case right here, and turn that into a one rational expression already. And so now here's a one thing. The reason we call this inequality a rational inequality because the left-hand side truly is a rational function, or the left-hand side came from a rational function. Okay, so now we're gonna observe. So now in this observation, I can see that I can let a rational function R of x be the x minus 2 times x plus 1 over x minus 1 times x plus 1. And so again, this is just observation right here. Yes, the whole thing is an inequality, but what I noticed after observing this inequality is that the left-hand side is a rational function, and that's why I assign that as a function. I define a rational function being the left-hand side. All right, and so that's the first observation we've done right there. Okay. And so now, so after that assigning this rational expression to be the function R of x, then we notice that R of x is a rational function. And you may notice, anyone learning in this video may notice that we have some common factor and all that. Yes, naturally you will start canceling out, but hold on to that. We will get to that stage where we cancel out the common factors, but at this point right now, let's just not worry about the common factor. Let's just not worry about canceling out the common factor. Okay, we'll handle that later. So right here, right at start, with the very original left-hand side being regarded as a rational function, the next thing I want to see is, and this is and like I said, all we need to know is that we are aware that there are rational functions existing, and that's why I brought up this observation right here. So now we know clearly that this is a rational function. So knowing that we have a rational function, the next thing, and this is also connecting to what I said earlier, we need to know what is the domain, or we need to know the domain of this rational function. Okay, so now at this point in our experience learning through the rational expression, the rational function quite thoroughly, then I am going to see that I'm not going to spend time solving, because we've learned that skill, so you take your steps there. But now clearly the domain here of this rational function is any value but exclude, anywhere exclude those x values being the zeros of the denominator. That's the only brief review I need to mention. So the domain is any x values other than 1 and x values other than -1. Okay? So this is admittedly not the formal way to indicate the domain, but this is a convenient way to indicate the domain, where you see the main problem here is not targeting at looking for finding the domain. Nope, that's not that. So we only need to understand that the domain of this. So it's not the answer to our problem. It's just part of the steps getting there. So I only need to write down the domain in a convenient way. The domain of this function is any x value except 1 and -1. Okay, so that's just the domain, even though admittedly, as I said earlier, it's not the formal way of indicating domain, because usually in these modern day domains are indicated in interval notation. But here allow me to use just that convenient notation, just that convenient convention. Just simply, hey, the domain of this rational function is any x values except these two. Any x value except these two values. Yeah. So we have to exclude x equals 1 and x equals -1 out of our the entire real line of numbers right there. Otherwise, anywhere else is going to work. That's the idea. Okay. Or we can just think about the line of numbers right here. Okay. And then -1 is a point, 1 is another point. We take anywhere else except these two. That's the idea right there about domain. All right. So now once we know about the domain, this is where we're going to start doing some canceling of the work. Okay, because I brought in this logical understanding when we were solving about the vertical asymptotes and wholes of a rational function. Okay, but the idea is that if we just simply cancel common factors away without considering the domain, then sometimes we may deceivingly, after canceling away some common factor, we may deceivingly think that see, this is a consequence. If we rushly cancel that common factor x plus 1 away, then our function will consequently become x minus 2 and x minus 1. If we find the domain after canceling this out, then this is in the end a different function. Okay, it's the two functions here are only equal if we stay away from these two values. And then this function on its own can be another function where the domain is only anywhere. The domain for this function is only anywhere not 1, but did not necessarily exclude this -1. And so if my bottom line here is that if we cancel the common factor in a rush before considering the domain carefully, we may leave out a couple critical values that need to be excluded out in the domain. We may accidentally forget about some of the values to be excluded from the domain. Okay, and that's the reason why. So keep in mind, anytime we're working with a function, a rational function, find the domain first. Nail down the domain before we start attempting any algebraic operations. For example, simplifying, canceling out common factors and all that. Okay, and so now back to the work that we're doing. Once we have successfully found the domain here, we are going to cancel the common factor. All right, so canceling out common factors must come after you nailing down the domain like that. And so now your rational function. Now we know that we permanently stay away from these two values, but then in that way we consequently can reduce the rational function down to this simpler version, this simplified version, x minus 2 over x minus 1. All right. So now on this board right here, now we're thinking about this r of x simplified down as x minus 2 over x minus 1. We're simplifying it down like that. So now this is our denominator, this is our simplified denominator, but this is the one that from this point we're going to apply our understanding from the polynomial inequality to make it work here. Okay, so this is the denominator. Of course, it's the denominator, the simplified. And then this is now the numerator. All right, this is now the numerator. So in this way, now this is what I'm doing. This is a factor of, in the numerator, it's a linear factor, only one of them. In the denominator, there's also one linear factor left. Okay, so after canceling out, we're going to look at the overall updated, at the final simplified rational expression and identify numerator and denominator. And then now we're going to identify all of the linear factors that's left over, that's really left over in our overall numerator, overall rational expression here. So in that way, now I'm gonna find zeros. So I'm gonna find zeros of the numerator. I'm gonna find zero of all the zeros of the numerator. So you see this, I said in the beginning of the lecture here that it's not necessarily directly relevant to learning about vertical asymptotes or the horizontal asymptote. Yes, it's still true, but the skills I'm doing here is also similar. It shares the same steps with some of those vertical asymptotes work that we were doing, and then finding intercepts like that. So in that way, it's never bad that you watch this idea after you have seen how I've done these steps back in the vertical asymptotes of a rational function or the finding intercepts of a rational function. But in the end, I can still repeat the steps here. So now as far as the zeros of the numerator, I isolated out the numerator here. We only have the x minus 2. So I'm going to set that equal to 0 because we want to find the zeros of the numerator. And then this is the only distinct linear factor. And so now that leads down for me, okay. So quickly solving that, I'm ending up by, I'm going to solve this by adding 2 to both sides. That's leaving for me x equals 2. All right, so that's the work. So now zeros of the numerator, I am going to have x equals 2, and this is the only one. It's a list now. It's a list of zeros in the denominator. Okay, now I need to erase this quick little steps right here, this quick little scratch work. All right, so now once we've found all zeros of the numerator, let's now advance to finding all zeros of the denominator. All right, so let's find all zeros of the denominator. And so now, again, it is learning anything time that you learn about a rational function, it is strictly a requirement that you learn about what a polynomial is, because all of those ideas come out from our learning about the polynomials. Okay, there is no way to learn to move on with a rational function or anything with a rational function before learning about the polynomials, because all of these terms here, the zeros or the horizontal intercepts of a polynomial function, you must be all familiar with that before we get to learning any of these. All right, so now as far as the zeros of the denominator, see, quick scratch work again. So now I'm going to take this final simplified denominator, which only has one distinct factor and one unique factor here as well. So x minus 1, I'm going to set it equal to 0. taking our step to solve for that, I'm adding 1 to both sides and leaving x equals 1 right here. So this is my 0 and the only 0 in the denominator. Other problems, after simplifying down the expression, we may end up with more than one the distinct factors within our denominator or within our numerator. Okay, but this is the generality. The idea is that we're going to find all zeros of the numerator and we're also going to find all zeros of the denominator. So now, and how many there are in each problem, it depends on each problem. Okay, so now we've found the zeros for the numerator. There's only 1, x equals 2. The zeros of the denominator, there's only 1, x equals 1. All right, and so now, and I can put away the steps. And all these steps here, I don't have to focus too much on that because you have seen it all from your days of learning about the polynomials. And so now, after successfully have seen all zeros of the numerator and the zeros of the denominator, okay, now this is where the idea that you have learned from the solving the polynomial, the inequalities come back. Okay, so at this point, hopefully that you have already learned and been able, been fluent with that skill, how you solve the polynomial inequality, because the central theme, the central method I brought in there will be used here again. We're going to use the sign chart methods, the sign chart methods. Okay, and so now that sign chart method I brought up when we were working through the polynomial inequality. Now I'm going to bring it here, and this is why I want you to be able to see how we have done the solving polynomial inequalities prior to this. All right, so as far as the sign chart, again, that idea is done as following. Just think about the whole line of numbers, the entire line of numbers. Okay, and then before I got too far into the steps here, let me remind anyone watching this video again that there is the whole point, there is a whole reason of finding the domain, which I just did not put it here for no reason. The point of listing down the domain here for this beginning rational function is that we got to constantly be aware that no matter whatever we do, we have to keep our x values aside from 1 and aside from -1. We can only find x values other than these two values listed here as the list of exclusion. All right, so let's get back to the other board and continue our work with that. So on this sign chart, imagine the line of real numbers. I'm going to put all zeros of numerator and denominator together in the increasing order from the left to the right. It's just the way. So you have seen this idea back when we were solving polynomial inequality. So we're going to use that exact idea here again. Okay, now we're just going to extend. So solving a rational inequality in a way how I see it, it's just an extended version of solving a polynomial inequality. We start out putting things, we have an inequality in factor form and we are able to find all zeros. So here we're going to even look at all zeros, including the zeros of the denominator. And then we're going to put them all together in our sign chart. So now increasingly from the left to the right, then in the line of real numbers, 1 comes before 2. So 2 is a spot out here somewhere. All right, so now after placing down the two values here in increasing order from the left to the right, and now that naturally breaks our entire line of real numbers into 3 separate zones right here. 3 separate zones. So formally we call those the intervals, 3 separate intervals. There's one interval that's anywhere x less than 1. There's this interval where x is meant to be any value between 1 and 2. And then there's this interval where it's indicating those x values are greater than 2. We got 3 separate intervals here. Okay, right out from this simplified rational expression right there, or rational function. And now we're going to do sign check. Okay, so now for that first interval from the left to the right, the line of numbers is right here, and then I'm going to use a dotted line right here. Okay, and so under the interval where x is strictly less than 1 right here, I'm going to pick a value. So that exact same method right there, that's the exact same philosophy or the logical reasoning of the sign chart comes back exactly the way how it was. So I'm going to pick a value less than 1. 0, for example. That works just fine. I'm going to substitute. So x equals 0 is just a value that we choose. Okay, I choose x equals 0. You can try, if you are watching this along with the lesson here, you can try independently a different value as long as it satisfies less than 1. You can choose -1. You can choose -5. Okay, the point now is that I am going to substitute this 0 into my rational function. So 0 for x, if x equals 0, then 0 minus 2 divided by 0 minus 1. I'm substituting that trial value into our actual rational function, the simplified version. It will work. Substituting that there, now I'm going to end up with a, primarily what's going on here is that we're looking at a negative sign in the numerator divided by a negative sign again in the denominator. All right, so now all together we're going to end up with the negative number divided by a negative number. Our answer there will come out being, so in this interval we know that we're going to end up with a positive sign. That's why I'm writing that in red ink right there. So positive sign, this is just the showing work, a little showing work right there. All right, so positive sign, so that means what? If you try a -2 or you try a -1, as long as you agree with me that you use a value less than 1 in this interval, your rational function will come out positive sign overall. And that's the whole idea of what's so-called a sign chart. We use a chart here to check the sign of our overall function, the rational function in that interval, in that zone right there, in that particular interval. Okay, and I chose x equals 1 to try. You can choose anything as long as it's less than 1. All right, so now in that same exact idea right here, why don't we, so I'm going to try, how about x equals 1.5 here for that interval. 1.5 for that interval. So now substituting that into our rational function that's already simplified right here. Because the simplified is the easier version. And all operations will work and will turn as long as we stay away from those values excluded from the domain. As long as we stay away from those, then see, these values are now all excluded away from the domains. Okay? We'll get to that. Okay. So now x equals x equals 1.5. So 1.5 subtract 2 divided by 1.5 subtract 1. So we really are looking at a negative value but divided by a positive value. That's tentatively what I'm looking for. I don't really care much about the actual value, but the sign on each of these parts right here. So negative value divided by positive value. So my overall answer, my overall sign of this interval, so that's just the scratch work right there. So my overall sign of this interval now is going to be now I'm running a little short at space here, so allow me to erase this little work. All right, and so now my overall sign here has to be negative sign. All right, it's negative sign for that. That's what matters for me. Okay, so the function will come out negative sign in this interval anywhere between 1 and 2. All right, and then let's move on to the next interval. So I'm going to choose, how about, see, we want x greater than 2. We want x greater than 2, so x is greater than, how about, I'm going to pick x equals 3. Okay, anything that's greater than 2. You can choose x equals 4, you can choose x equals 5. Okay, and so now what I'm looking at is 3 minus 2 divided by 3 minus 1. Okay, minus 1. So it's giving me a positive answer on top divided by a positive calculated value at the bottom. My overall sign of the rational function here is a positive sign. Positive divided by a positive gives me a positive sign. So now I am just right around the corner for getting that final answer right here. Remind yourself again. Initially, or ultimately the question is asking which values, when it's solved, anytime we're solving an inequality, we have to end up with multiple values. Okay, so which values of x make this rational function negative? Reading that inequality as less than 0, but it means a negative. Which values? So now we have a whole interval of values. Which values? So now think about the sign chart. Which interval makes our rational function here negative? All right, because this is rational function. Yes, that's just the simplified version after we have considered the domain carefully. So that's a simplified function, making it easier for the computation. Okay, but now let's go over there to the other board and find out our answer based on the sign chart right there. So, which values? This interval of values for x is making it positive, making the whole rational function output value positive. That's not what we want. This one right here, okay, anywhere x greater than 2, this entire interval, we now using the sign chart, we know that the function outputs will come out positive. This interval is not what we want. The interval we want is here, anywhere between 1 and 2. Anywhere between 1 and 2. Okay? And so here's the logic. Okay? If we're looking a little more closely in the beginning problem right here, we are looking at a strict inequality. Now, in my style of teaching this the rational inequalities business right here, allow me to classify those inequalities without the equal sign as one subclass of problem. And then once we're all fluent with this, we're going to take that idea and move on to those classes where the inequality comes with equal signs. So right now, throughout this demo problem and maybe a few other example problems which I will deliver later on, I'm only going to focus on those where it's strictly, it's a strict inequality, no equality involved right there. Okay, so that means we don't have to worry about including any value. So the interval that we found is being a negative interval. It's satisfied right here, the requirements. That's our answer. All right, so now let's have a look at this. So this is now going to be our final answer right here. Our final answer here is going to be the interval from the anywhere between 1 to 2 right there. All right, so now as far as the answer, I'm swinging back to this board space right here and utilize this little amount of space. So now as far as solving the answer right here, indicating the answer now we have to write the answer in formal interval notation. So now we're looking at anywhere between 1 and 2. So that's our interval. All right, it's an interval. Anywhere between 1 and 2. And though that is completely parentheses is around, okay? Open inequality, or we're excluding the two endpoints of the interval. We only take anywhere between. That's our answer for this case right here. All right, so the same demo problem right here. Before I'm rushing in, and before we're rushing into any example problems right there formally, so that we can carry out a step. Okay. Let me use the exact same rational function here, but produce a completely separate, completely different inequality. All right, and at this point, once we're done, you will understand the reason why when I teach this, I want my students to retain or stay with the original before simplification and then find domain first. Allow me to introduce my reason right here. Okay, so what if our inequality was a greater than? So the one I brought up earlier was done, really done. That demo one right there, the one where we had this left-hand side being negative, less than 0. That was all done. We found our answer. But now this is really, it looks almost exactly the same, but just because we switched the inequality, it's a completely brand new problem. Good news, there will be a lot of information we can retain. But definitely, this is not the answer. This is the answer where the left-hand side of rational function is negative. Now we're looking for which intervals is making our rational function here positive. Okay, so definitely I cannot retain this answer. But now the good news is all of that information stays the same. We can still retain all of these information because it's still, first of all, it's still the same rational function. I just simply, once again, the easier kind of problem is here in a sense that we already had all terms on the left hand side and leaving just either a 0 or just a 0 actually on the left, on the opposite side. And then furthermore, we have already successfully put it all in one rational expression and put them in all factor form. So in case some of your problems did not come with the factor form yet, spend some time factoring out the left-hand side rational expression, both top and bottom. Okay, but we'll get to that later. And so now once you've had the rational function defined here or recognized here, okay, then we're gonna go ahead. You can see that. So now this is the second demo problem. It's not an example yet, but you can kind of see that this step right here, after defining your rational function, this is really, as far as getting into solving it, this is really big step right here, and I can call it step number 1. It's the first out of all. Okay, because this thing here, somebody somebody can write it, somebody doesn't. That's not important. Okay. After we recognize the domain, yes, the work carry on. We're gonna simplify. See, that's why I'm still having the simplified symbol here, and that comes out for us. And so now, yes, we know it's a rational function. Allow me to write down see, we simplified it down to x minus 2 over x minus 1, and that's the reason why this work is still here. And now once again, this is the updated, the simplified rational expression after we cancel out a common factor. So now x minus 2 is numerator, x minus 1 is the denominator. Just exactly like how I was doing that demo problem earlier. We're going to go ahead and find all zeros of the numerator and of the denominator. Okay, so canceling out your common factor is really step number 2 right here. This is the beginning of step 2 right there. Because we get all of those cancel out, making the work easier for us. But only do that after you have nailed down successfully your domain of the function. Okay, and then after this point on, after you have identified the domain of your rational function, make sure that you are fully aware of those values of x that we're excluding from our function right there. Okay. And then after simplifying, yes, the simplification work right here, the simplifying work is making it possible to find all zeros, is making it easy to find all zeros of the numerator and of the denominator. So I can legally see this as step 3 right there. And you see, I could have also emphasized these steps right here at the end of the first demo problem right here, but allow me to now, once you see it sort of like the second time, now I can show you that because in the end I'm going to repeat exactly all of those steps. So now it's time to kind of also summarize all of those steps like that into the numeric stages like that. So step 3 is here that we get all zeros of the numerator and denominator, and these steps are written in red ink for a good reason. They are important, okay, and quite universal. And now once you've had all zeros of both numerator and denominator, we're going to build the sign chart. So the sign chart is legally now your step number 4 right there, that big step number 4. So we built our sign chart, and the way how the sign chart works is exactly the same. And so like I said, it's a different problem. It's a different problem in the sense that from the earlier problem as the demo problem, I use less than. I want to find the interval or the intervals of x, making this rational function negative. But now it's a different question. We want to find all x values, making this rational function positive. That's why I erased the answer. But surprisingly, all that work stays the same. All right, and so now, knowing clearly that we have a completely different goal now, we're looking for those intervals of x, making our rational function here positive value. So now the sign chart, which is still retained here, is having all of that idea. Having all of those answers for us. the first interval here, anywhere in that interval where x is less than 1, anywhere in this interval is going to, for any x value in this interval, it's going to make our rational function positive. So that interval here answers our question in the beginning. But that's not all the interval. Remember, recall for yourself that once we have built this sign chart here, in the way it is, due to the number of zeros we have found, after putting our rational function in simplified form due to the number of zeros, both from the numerator and from the denominator, we naturally broke this line of numbers into 3 separate intervals. 1, 2, and 3. 3 separate intervals. So that intervals there, yes, it answered our question. But was that the only one? This one here obviously failed because this interval made our rational function here negative. So we don't want that one. But we will definitely include this one as well. We will definitely take this one as well because this interval indicating for any x values anywhere above 2, this interval will make our rational function positive in the output. So now indeed the answer for this interval, the answer for this particular problem is as following. Anywhere between minus infinity and 1. Okay. And then we're going to union with anywhere between 2 and positive infinity. So we believe we came to the answer. We believe we came to the answer. We follow exactly, we follow really closely and side by side with the graph like that. I mean with the sign chart like that. Okay? And that seems so far that we've found the answer. Okay? And so all of that work stays the same. But now when it comes to, this is just something we constantly have to be aware of. And I also mentioned this when we were doing the first demo problem. And here everything is exactly pretty much the same. Simply switching the inequality here is throwing us into a completely different problem. Even though the good news we had for us was all of that steps can be retained. Can remain exactly the same right here. But now as far as the final answer, there was a reason why I said once you found your domain right here, be fully aware about the domain. What needs to be excluded from the domain. Ladies and gentlemen, I'm not saying that this is our correct final answer yet. We're 99% close, but this is still not the correct final interval yet. Not the correct final answer for this inequality yet. That's why I didn't put that in a box or anything like that. Okay, so here's the thing. Here's the reason. Let's tackle down right here in this first interval from the left to the right. Okay, it's in the way it is. These are the intervals, yes, admittedly right from the sign chart, these are the intervals that answer our question. But there's some little extra details that now we got to bring it in. That's why our awareness of the problem will count a lot. We have to constantly exclude these values, x equals 1 and x equals negative 1. We have to always exclude those two values out. From the left to the right, this value x equals negative 1 comes first on the line of numbers. X equals negative 1 indeed stays inside of this interval. X equals negative 1, the value we need to include is indeed somewhere right in that interval. Okay. So that means we cannot just simply take the whole interval here. We have to give it a break. It has to be a broken up interval, as a matter of fact. So after that logical reasoning, feel free to pause maybe the video and rewind to catch my explanation. Simply because we are constantly aware that our domain of this function exclude x equals negative 1. But x equals negative 1 is still a member in this interval. It's still a value in this interval. This interval came out from our sign chart from the other board. But x equals negative 1 is unfortunately still inside of this interval. So we have to adjust our interval as following. Alright, so now I'm going to have to erase and correct the answer as following. I'm going to go with an interval anywhere from minus infinity to negative 1. That's one interval because I'm excluding negative 1. So even though, technically anywhere less than 1 we'll answer our question, but -1 unfortunately is in here that need to be excluded out. That's why now this one interval is broken up into two separate intervals, and one is from -1 to 1, -1 to 1. All right, -1 to 1. And then so now our real answer is here. Our final correct answer is here. So the reason I didn't mention that, and now I mentioned it anyway, x need to also be the 1 also needs to be excluded from our domain. X equals 1 also needs to be excluded from the domain. But look at x equals 1. It's not in this interval. It's not in this interval from the sine chart. It's neither in the other interval from the sine chart. So we're good. We're good. We don't have to worry about this one. So we were fully aware that we need to exclude this value the whole time. But this is the only thing that impacts our final result from the sine chart. All right, so laying down the foundation about the domain is extremely important here. The sine chart idea is still coming through, but then at some point here and there, see in the earlier demo problem, we didn't have to worry about any of this because the interval we found completely away from these two excluded values already. But now be aware in some other problems, simply in the very same problem right here, changing the inequality. The value that we need to be aware about to exclude, it's already in one of our intervals of the answer. So we need to also exclude it out. And that's how it's explained for this broken up interval right here. And this is now our final interval. 3 separate broken up intervals right there. All right. So at this point, that is enough with all the demonstration right there. Okay. Really, it's one rational function, but I brought up as 2 separate demo problems right here. And now we are ready for our first formal example. And now, after doing some formal examples about all of these inequalities, now recall again, my main aim right now is focus. My students focus, viewers who learn with me on those inequality where it's a strict inequality, no equality comes along, no equal sign comes along. Because this class of rational inequality, this subclass of rational inequalities is more useful for your calculus level later on when you take the formal calculus course. But then later on, the kind of rational inequality where it looks kind of similar, but having equality comes along, you won't see it as much. That's why, I still teach those in the same lecture here, but we won't have as much applications out there. All right. And so now let's drive that into our example. All right, so our first example, and allow me to keep this lecture here as a separate lecture, even though it's about the rational the functions still, but I would like to keep that as a separate lecture. So I'm restarting my example numbers here. I'm starting with example 1, okay, to begin with. So now we just want to solve, okay, the following rational inequality. All right, for x. Okay, and I'm about to give a few different problems. So each problem has its own things that we need to pay extra attention to. But now, example is a good place where anyone viewing along can start practicing your skill right there. And you're gonna repetitively see how I repeat those steps that were introduced, okay, as a formal instruction, as a formal guideline. How I can repeat those steps introduced in the demos in any of these example problems. That's the whole idea of any of my examples so far throughout the entire learning time together. Okay, and so part A. How about let's look at the following inequality. How about x minus 1 over, and then here I have x minus 2 times x plus 1, and I want this to be greater than 0. Greater than 0. Okay, and again, so you can see ahead of time a little bit that my intention that the entire example 1 as one class of problems, we only focus on those inequality where there's no equal sign involved. Okay, just strict inequality, either a greater than or a less than. And then again, we only need to focus on those simpler kind of problems where the rational function or the inequality has already been rearranged in a way that everything's non-zero is moved to one side and the opposite side is simply a 0. We just want to find the x values that satisfy left hand side here is greater than 0, or this expression here is positive. All right, and then also it's still easier in the case that we didn't have to factor any of these part right here, because your rational, the function here already came factor. Numerator and denominator are in factor form already. All right, so now we're going to start repeating those steps that I introduced right here. So the first easy thing, now I'm going to recognize that I can see that, hey, we can let R of x be a rational function that is x minus 1 divided by that x minus 2 times x plus 1. So all that entire left hand side can be regarded as a rational function. That's just having that step or not too important, but I also recommend having that step. It gets your work organized. All right, and now once we've successfully recognized our inequality having that rational expression in there, okay, now really the first formal step right here, we get the domain. Okay, and now from your experience at this point, I'm not going to waste your time keep explaining about how to find the domain. The domain come out from this function is easily just one of them is x. We need to exclude x equals 2, and then the other one we need to exclude x equals negative 1, because these are the zeros. These are the zeros of the denominator before any kind of simplification. Before any kind of simplification, in case you recognize any common factor and you are so mentally ready to cancel those out, the domain has to be anywhere except those values that gives a 0 in the denominator. That denominator before you attempt to make any cancellation of common factors. Keep that in mind. Okay, and gladly this problem does not have any foreseen cancellation that can happen, and so this is the only denominator we have. Okay, and so that's the domain. We can work this function. We can work with any x values excluding these two. So now have a full awareness of that along the way. And so now this is step 1. So step 2, we're going to start canceling out common factor. There's none this time. Anyone viewing this video is mature enough in math to see that there's no common factor to be canceled here. So we're good to go with step 2. Step 2 is kind of done. So step 1 is here. Okay, that's step 1. We're done. Step 2 didn't need to be done, and didn't need to get that taken care of because the function has already been simplified. Okay, and so step 2 is kind of like done right there. Okay, and you don't really have to write down these ridiculous checks right there. And now once we're done with step 2, allow me to move on to the other board. All right, so now with our current rational function, so now I'm going to find all zeros of numerator. The numerator. All right. And so now recall again that our rational expression, our rational function is here. And this is already the most simplified we can go. All right, so now in its most current numerator, x minus 1 is the only the linear factor in our current simplified numerator. All right, so there we go. We're going to quickly set that only and the distinct and the only linear factor in our numerator, set that equal to 0. And 1 to both sides. Right, that leaves me x equals 1. So this is the only 0 of the denominator, of the numerator. So now I'm going to write that here as a list. Okay, showing this work or not at this point is not important. So that was just scratch work right there. This is what's important. Okay, I just now listed down all zeros of the numerator. All right, let's advance to now zeros of the denominator. All right, all zeros of the denominator. So for denominator, we found in its most simplified form of the rational function here, we found two distinct linear factors. Okay, so I'm still going to repeat the steps, the little sub-steps again, even though when you actually you're at this point learning in this lesson right here, you should be a lot more mature in that. Okay, so one distinct factor in the denominator, in the current denominator, is the x minus 2. I'm going to set that equal to 0. Another distinct factor in the denominator here is the x plus 1. I'm going to set that equal to 0. If we have any multiplicity, that's, when finding the zeros, multiplicities don't count. Okay, any of the multiplicities doesn't count, but it counts for other purpose, like that. Not this kind of purpose that we're doing. So now finding the zeros here of the denominator, for this sub-equation on the left here, I'm going to add 2 to both sides on my left column. Okay, and then so here x equals 2. So I found one of them, x equals 2. I'm making a list. I solve and I make a list at the same time. So now x plus 1 equals 0. Solving for x, I'm going to subtract 1 from both sides. I ended up with x equals -1. So x equals -1 is another one. Okay, so like I said, if you're a student learning directly from me, skipping this step is completely okay right here, because right now what's primary as a step here is this. We're listing down all zeros that you can find for the numerator and for the denominator. These can be left on a scratch work right there. All right, but it never hurts to document all your steps. Okay, the more details you can show, the better it secure your work right there. In case any errors come out, you can easily trace back where the error came from. All right, so now these are the zeros of the numerator and the denominator. We got 3. So now it's simply time for the sign charts. Just time for the sign chart. So now I'm going to put in the sign charts. And it's going to be done as following. The entire line of real numbers. Okay, allow me to draw that a little big. Here we have 3 separate values. So from the left to the right. And so when we when we place all of these zeros of numerator and denominator together on the line of values, then we just have to follow that order, the increasing order from the left to the right. So whichever the smallest values, the lowest value has to go on the furthest left, and then we keep putting higher value to the right hand side. So -1, the lowest of all 3, it's there somewhere, and then 1 is somewhere here, and 2 is somewhere out here. Okay, and then I just now realized I didn't leave enough space for myself between the 2 values here. So indeed, this one is a little too close, and then 2 is here, so 1 is here. All right, so now this line of real numbers now is broken into 4 separate intervals, just the way it is. All right, and so that now we have a chart that splits our board into 4 separate columns right here, ready for a chart, a table kind of thing. Okay, and then this is x less than -1. This is x between -1 and 1. Okay, and this is x between 2 and 1, and this is x greater than 2. We got 4 separate intervals, 4 separate zones of values to work with. All right, so now that idea of sign chart just kicks in again. So now I'm going to pick a value. For x less than -1, we can pick x equals -2. How's that? Okay, it will work. Okay, it's a value that's less than -1. And so now substituting that into our function here, so our rational function in this case. And I should have written that on this right board, but I didn't. I want to save some space. So this is our R of x. Its most simplified form after we have identified the domain right there. So with our current rational function here, All right, so now I'm going to have minus 2 minus 1, and I'm dividing that by, so now I'm looking at negative 2 minus 2, and then negative 2 minus 1. All right, so I'm about to do so. I'm very short at space here, no matter how much more space I've spent for the sine chart, but I'm still short of space. So allow me to just indicate the overall sign. So be aware, or maybe I can use this little space that is still visible on the screen here. You see, the numerator will be in this way. How I see it, the numerator will be negative. That's what comes out from the numerator. Okay. The denominator, this is, you see, this is the reason why knowing the domain is a good idea. The denominator, this is negative 4. Okay, it's negative 4, it's a negative value, and then multiply in products with another negative value. Okay, so negative value in products with another negative value. Okay, that's all that the two negative signs are multiplying together, because negative 2 minus negative 2 minus 2 is negative. Negative 2 plus 1 is another negative. So two negatives multiplied together. That's how I had that setting right there. So that means altogether this overall setup here must give me a negative value, okay, for the entire rational function in this interval. Anywhere for any x value in this interval, the rational function will come out negative sign. That's why I wrote it in red ink. This is just the workout solution like that. All right, let's move on to the next one. So now in the middle interval, I'm going to say let's pick x equals 0. Okay, it will work. It's not violating our domain right there. All right, it's not violating our domain. And that's the reason why we constantly have to be aware about what's our domain, what's in our domain, and what's excluded from our domain. So I chose negative 2 here earlier, and I knew it was not, it was in the domain. I chose x equals 0 here, and I knew it was not, it was in our domain. It was not excluded or anything like that. Okay, and so now I'm looking at 0 minus 1 and divided by here 0 minus 2 times 0 plus 1. All right, so as far as the worked out solution, this is negative sign, this is negative sign, and this is positive sign. So it's going to be a setting like this: negative divided by, in the denominator, a negative times a positive. All right, a negative times a positive. So that means overall, in this interval, our rational function turns out to be positive sign overall. The output of the rational function has to be positive in this, for any x values in this interval. All right, so that's how we take care of the second interval from the left to the right. The third one, so now anywhere between 1 and 2. So how about we can pick x equals a 1.5, for example. So now 1.5 minus 1, and then we're dividing that by, so now minus 2, and then plus 1. So it's a 1.5 here substituted in for x, 1.5 substituted in for x. Okay, it's positive here now. It's positive in the numerator, and then in the denominator we're having two factors. One of them is negative, the other one is positive. All right, it's negative here for that factor, and it's positive here for this factor. So now my overall answer here, my overall sign here of the rational function in this interval is positive. It's positive. Okay, and so now the last interval, we are so ready. So we can pick x equals 3. Okay, and then anyone viewing along with the lesson can also just pick your own try out values like that. Okay, as long as it's in this interval. And so now here I have 2 minus 1 divided by, in parentheses is minus 2 and plus 1 here. How about so, and actually it should have been 3 here. Okay, so 3 minus 2, 3 plus 1. So now you can easily see that it's all positive here. Because it's positive here, it's positive for that factor, it's positive for this factor as well. So together it's positive sign. So the sign of your rational function outputs is indicated in red ink here for this sign chart. So now we are ready for giving our final answer. Okay, but again, be aware about what x values or which x values need to be excluded from our domain right here, because it will come back. Okay, so now I'm going to navigate to the other board and look at the function. Our rational function is here. The inequality is looking for the rational function's outputs to be positive. That's what greater than 0 means. So now all we have to do is just look it up from our sign chart right there. All right. And then I should have mentioned listing down all zeros from the numerator and from the denominator. This was our step 3 right there, formally as a step. And then the sign chart here, the sign chart work is step number 4 right there. All right, and then so now once we've had our result, our sign checked result right here, we want positive intervals. We want intervals where our rational function outputs being positive. So that's the interval. One of them being anywhere between -1 and 1. I just now realized I had a typo here. And so this must be negative for that interval. All right, and so now for the actual answer, it's only these two disconnected intervals right here. One of them is between -1 and 1. The other one is greater than 2. All right, I apologize for that minor typo earlier, but now gladly I caught it in time right there. Okay, so now here's how we write our final answer. So as far as the final answer, minus anywhere between -1 and 1. That's one interval. And then we had another one anywhere above 2. So anywhere between 2 and positive infinity. That's another one. And we use a union between them. Okay. But so now learning from the experience we have seen back in the demo problem right there, then we got to also make sure that our excluded values from the domain right here is not anywhere in these the values that we're supposed to exclude, the x values that we're supposed to exclude. We just want to make sure that they are not anywhere inside of any of our intervals here. And obviously they're not. X got to be other than 2, but 2 is already excluded. Way to go. X got to be other than -1, but -1 is already excluded due to that parentheses nature right here. So now we know that this is our final answer. All right, so this is our final answer. The interval that makes our inequality positive, the intervals that make our inequality, our rational function positive, it's those two intervals together. We put them as a union there between them. All right, let's now get on to another problem right there. And then at this point right here, once anyone already got quite in gear with the direction right there and got quite engaged into the solution, the methods, it's such a definite method right there. Okay, and now we can start picking up pace a little bit. All right, so now let's look for how about part B of our problem right here, of our example. So how about x plus 2 all square times in product with x minus 1 all over, and then this is x minus 3 times x plus 2. We want this to be less than 0. We want that to be less than 0. Okay, less than 0. Okay, so now once again, this is the simple case in a sense that we already brought all non-zero terms. We already finished rearranging the inequality to the point that everything non-zero stays to one side and the opposite side is 0. So we got that. So in some other problem, which is slightly more challenging, but all it does is take some of your challenge, some of your patience. That's all. And then another thing that's making it the simpler kind of problem is that it's already came completely factor for you. Numerator and denominator are in factor form. Okay, so that's another easy point. Otherwise, if any of yours a rational function did not come with factor form, then spend some time factoring out both numerator and denominator beforehand. That would be the best idea. Okay, even before you try to find domains and all that, because domain is the formal first step. But then if we have to take any sort of like a preliminary step like that, so do it. So factoring out completely is what I consider as a preliminary step. Okay, so now here I recognize my rational function being as this x plus 2 all square, everything on the left hand side of the current inequality, all over x minus 3 times x plus 2. And this is where it aligns with that. This is where it aligns with that demo problem I had earlier. We have some common factor that potentially, I'm only saying potentially, can be simplified away. But right now, as of this point, when I recognize this as a rational function, I am keeping it the way it is before canceling out a common factor. All right, before canceling out a common factor. And so now in that way, really first step here is to tackle down the domain, because without canceling it too rush, like that, without canceling it too rushly, then we can find the domain most properly. All right, without worrying about skipping some values to be excluded. So now we really have two distinct linear factors before cancellation. We have two distinct linear factors in the denominator here, which gives 2 zeros in the denominator. 2 zeros in the denominator. And those will be the values excluded from our domain. So our domain here must be anywhere except x equals -2 and except x equals 3. All right, and anyone viewing the lesson here, the lecture here should be mature enough for me to pick up fast pace on that. All right, so again, in order to work with this function, including the cancellation work, we are only able to do that anytime we're looking at x values, looking at x values anywhere other than these two values like that. Okay, cancellation will work anywhere except these two x values, cancellation or anything else, calculation and all that. All right, and that's the whole point of a domain. And so now, once we've found a domain, then we can, because we know that we stay away from x equals -2 and x equals 3, and now we can cancel. So I notice I have this factor that can be canceled, but it only cancels once with that. Okay, and so we have a leftover x plus 2 right here. That's writing it down just sort of like scratch. So our final simplified rational expression is here. It's an x plus 2 over x is an x plus 2 times x minus 1. The square power was gone, and now divided by x minus 3. This is our final simplified rational function, ready for action right here. All right, and so now in this case right here, I'm going to use my other board for getting the work done. All right, so on this board of mine, again, I need to erase. So we've had the step 2 down, in a sense that we have already simplified our rational function. So now let's get ready for step 3. Step 3 simply is asking us to list the zeros of all zeros in the numerator and in the denominator. So, well, numerator, we had the only numerator. I mean, we actually have two distinct linear factors in the numerator. So we have one of them is x plus 2. We set that equal to 0. See, this is scratch work. Okay, and then the other one is x minus 1. We set that equal to 0. So this one here, solving for x, we're subtracting 2 from both sides, and that's ending up with x equals -2 for us. X equals -2. X equals -2. With this one here, I'm adding 1 to both sides. Okay, that's leaving for me x equals 1. Okay, so this is another 0 in the numerator. Okay, and this is really, I'm treating that as just scratch work. So now I can just take it away. And now moving on to the zeros of the denominator. The only linear factor we found, and the distinct and the only distinct one, is the x minus 3. I'm going to set that equal to 0. Back to the simplified rational expression. That's only linear factor in the denominator is there. All right, so in order to find the 0 for that, x minus 3 equals 0. X minus 3 equals 0. And so now solving for this, adding 3 from both sides is going to get me there. I'm going to have x equals 3. So this is a 0 of the denominator. I'm listing it here. All right. And so now after successfully listing down all zeros of the numerator and denominator, okay, after successfully listing down all of those, now we're ready for the sign charts. All right. So this is the end of step 3 right here. And I don't think we need to. I don't think I need to keep writing it. So now here comes the sign charts. All right. So the sign chart, the entire line of real numbers is here. Okay. We have a -2. We have a 1. And we have a 3. 3 values. Arranging them on the line of numbers from the left to the right. That's how they look. Okay, and then 3 values here will break the entire line of real numbers into 4 separate intervals. So this interval here is for any value of x less than -2. This interval here is for x between -2 and 1. And this interval here is for x between 1 and 3. All right, and this interval here is for x greater than 3. All right. And so now I'm going to create the columns here. Each interval is a column for me to do a sign check and all that. All right, so now I'm going to pick a value in this very left interval. I pick a value, you can pick a different one. All right, and so now again, be fully aware about what x values need to be excluded from your domain of this rational function. So now I'm picking a value for x less than -2. Okay, so though -2 itself was already excluded. So we want x less than -2, and it has nothing to do with the other one, so we're good with any value in this interval. Okay. And so now I'm going to pick x equals -3. And see, double check again, this value is okay. It's okay with our domain right there. All right, so now that means I'm substituting this into the function. So again, I have to switch back to the other board. So our final rational function is here. This is the one that's making it easy to determine sign behavior and all that. Okay, and so now I'm going to go -3, okay, plus 2, and then -1, and then all over some -3, so -3 is here, -1, and then -3 is there. All right, so that's how I just simply substituted the value I picked that satisfy less than -2 into the rational function. So I'm looking at the following sign calculations, just the calculation of the overall sign. I don't even need to worry about final value. Negative for the first factor, negative for the first factor, also negative for the next factor in the numerator, and then divided by, in the denominator here, also a negative factor. So now negative times negative is positive on top, divided by a negative in the denominator. My overall sign of the function, of the rational function, is negative sign. And now I'm writing that negative sign in red ink right there. Negative sign. All right, so that's how it's done for the first interval. Let's move on to the middle interval. So here, I mean the second one from the left. So how about we can pick x equals 0. Clearly x equals 0 is inside of this interval. And it's not violating anyone in the domain right there. It's a value in the domain. It's not -2, it's not 3. So this x value is good. All right, so once we had our domain down, anything we're doing in the steps after finding the domain, we got to fully be aware that whatever we're doing is compliant with the domain. Compliant, okay, with the domain. All right, so now I'm going to substitute x equals 0 into my expression. So let me just write it down first. This was supposedly -1. So now it's 0, 0, 0 here. All right, so that first factor here is a positive sign. And I don't think I need to write the 2 right there. So it's just positive sign. That next one here is a negative sign, but that next one, I mean the one in the denominator here, must be negative. All right. Negative sign for the one in the denominator. So now my overall sign of the rational function here is a positive. It's positive here for all that. Okay, it's positive. And now we are ready for the next one here. Okay. And so now I'm going to pick x equals 2. And again, see, x equals 2 is not one of those values that need to be excluded from the domain. So we're good to go with this. Okay. So anywhere we move, anywhere we go, we got to comply with the domain of our function. Whatever we do to the function, we got to comply. We have to stay in compliance with the domain of the function. Very important idea right there for any rational function. So now, this is plus 2, this is minus. So substituting 2 in there, I have 2 plus 2, okay, and then 2 minus 1, and then I have 2 minus 3. So now that means as far as the sign calculation, the first factor in the numerator gives me a positive sign. Second factor here is another positive sign, but the denominator here gives me a negative sign. All right. I didn't need to have that value. Just okay. So now my overall sign of the entire rational expression here must be negative. All right. It's negative like that. Okay, so it's negative, and so now with the last one here that I'm doing, so I can pick x equals 4. Okay, x equals 4, and now I'm looking at just like that, plus 2 minus 1 minus 3. So here it's 4 plus 2, 4 minus 1, 4 minus 3. So these are all positive. So now needless to do any calculation, I can see that my overall sign here has to be positive for this last interval. So negative interval is the first interval, and then the positive for the middle, for the next interval to the right, and then negative for the third interval to the from the left to the right, and then fourth interval is a positive sign like that. All right. And so now this is how we can use. This is what we can use to answer our final question right there. So the question is asking, we want to find the interval or the intervals, making the left-hand side as a rational function here negative. This rational function, once we have considered the domain, is reduced down, is simplified down to this. Okay, so now as far as finding the answer, that answer our need right here, the rational function being negative, then being negative, the sign chart has all of those answers. This first interval is negative. This third one from the left is another negative right here. All right. That means now I am going to finalize my answer right here. So now as far as the answer I've found two intervals. One of them is minus infinity to negative 2. I mean between negative infinity and negative 2. And then I have another one between 1 and 3. Okay. And then there's a union between them for now. All right, and then let's carefully check. Will any of these intervals contain the values we excluded Not the case here, not the case here. So we're good to go. We're good to go with that. So now this is our final answer. So again, initially we write down all the intervals from the sign chart right there with unions between them. But then before we put it in a box, we got to make sure any of our intervals there has, or we have to make sure any of our intervals there does not contain the values we excluded from the domain. If it happens, then we have to take it out and break one interval down to a separate two disconnected intervals. Okay, but that's not the case here, so this is our final answer right here for that. All right. All right, so now let's get ready for another problem. And this is the last one for this particular example right here. Okay, so part C of the example. So let's look at, we want to solve the inequality, the rational inequality x minus 1 in parentheses times x minus 2. Okay, and divided that by x minus 3 times x minus 1. We want that to be about greater than 0. Okay, we want that the left hand side to be positive like that. Okay, and so now we have done this quite a few times, including the demo problem, so allow me to start picking up the pace even further right here. So I recognize that the left hand side can be regarded as a rational function. R of x equals so x minus 1 times x minus 2, okay, and then divided by that by x minus 3 times x minus 1. We noticed, we found out, we spotted common factor that can potentially be simplified, but let's hold it at this point. Let's hold it at this point. So now the domain, as far as the domain of this function. All right, we can easily see that. So see, that's why domain is always the first step done before even simplifying the common factor away. Okay, because the domain will also exclude those even though it can get cancelled away. All right, so now to find the domain of this beginning or initial rational function here, we just look at that big denominator here. We recognize two factors. As I said, admittedly, this one here is ready for cancelling away, but before cancelling it, these are the two distinct linear factors in the denominator, causing zeros to the denominator. Okay, so now in that way, with these two distinct linear factors, I have x equals 3, it's one value to be excluded. I'm excluding that. The domain also exclude x equals 1. So the domain for this rational function, before you can even simplify, if you want to simplify, we have to simplify only for x values other than 1 and other than 3. So we only work with this rational function other than 1 and other than 3. All right, now we have the domain successfully nailed down. That's the end of step 1 right there. Now we can go ahead, because now we can assume that we can work with this function here completely away from these two values excluded here from our domain. So when x equals 2, we can do the cancellation. When x equals 5, we can do the cancellation. When x equals 1, we cannot. And that's the idea right there. So now assuming that we already excluded these two values, then I'm cancelling out the two factors here. Okay, so now it has x minus 2 divided by x minus 3. This is the final simplified one after we track down the domain. So this is the end of step 2 right there, simplifying our rational function. Okay, and so now let's get on the other board and get our steps down right there. All right, so now the next step here is to identify all zeros at the numerator and in the denominator. All right. So in how I see it, for the numerator, at this final simplified rational expression, x minus 2 over x minus 3, that's our final simplified R of x right here. Okay, instead of swinging over to the other board, allow me to just write it on scratchwork right here. So this is the only numerator, the only factor in the numerator. So now to find the the zeros of the numerator, I'm going to go x minus 2. This is scratch work. Set that equal to 0. Okay. So now solving for x, I'm going to add 2 to both sides. X equals 2. All right. So we found 1 and only 1 0 for the numerator. All right. So now let's move on to the denominator with our function now. And I just accidentally erased it, but I've left it there long enough. So now you should remember. X minus 3 equals 0. That only linear factor. I'm going to set it equal to 0. And I'm going to solve for that. I'm going to add 3 to both sides, giving it x equals 3. So now x equals 3 is the zeros of the denominator. We've had that there. All right. We have that there. And so now, once we've had it, both zeros, once we've successfully listed all zeros of the numerator and the denominator, now it's time for the sign chart. So this is the end of step 3 right there that we have successfully completed. Okay, so now we are going to construct the sign chart. All right, we're going to construct a sign chart right here. So just like that, same idea. We have 2 values, but arranging these on the line of numbers. From the left to the right, 2 comes first, 3 somewhere to the right-hand side. All right, and now this interval, and then that means that naturally our entire line of real numbers is broken into 3, 1, 2, and 3 separate zones, or 3 separate interval, the 3 separate intervals of values. All right, so the first zone here, the first interval here is any x value less than 2. This interval here is any x value between 2 and 3. And this interval here is for any x value greater than 3. All right, so now once again, let's create. And so at this point, since we're almost finished with all this idea, anytime we're solving those inequality, those rational inequality with these zeros and placing these zeros on the chart right here, I always leave the interval as open interval at start. I always leave the interval excluding these zeros out, even though maybe they come from the 0 in the numerator, or maybe they come from the whatever else, but we always start out by excluding them, and then if we can include them, we will. And that kind of problem will come in the next step. Okay, but for now, the inequality, again, it's only the strict inequality. So we never have to worry about including these, pretty much. Okay? So now, I'm going to pick a value. Here I can pick x equals 1, for example. X equals 1. All right. And I know immediately I'm going to fail with this one, because x equals 1 must be excluded from the domain right here. And so, yes, a lot of time we're eager to try values. But be careful with the way how we're doing it sometimes. Okay, because being too eager to try values, maybe it's satisfied here, but we constantly gotta be aware about our domain. We have to always be fully aware of what's excluded from our domain. X equals 1 is excluded from our domain, and so I just want to show that process, that in case we accidentally chose a value, but oops, it was excluded from the domain, choose a different one. Even though x equals 1, yes, it's in this interval, but it's the one being excluded from the domain. Choose a different one. All right, so now I'm going to go with, how about x equals 0? All right, and you can still pick another value that's still safe in the domain. That's still in the domain and in this interval as well. All right, so now here's how I'm seeing it. In my final simplified rational expression, which is the x minus 2 over x minus 3. This one here, x minus 2 over x minus 3. Okay, that final rational expression there. So now I'm going to go 0, minus 2, and then minus 3 in the denominator, so 0 minus 3. 0 minus 2 over 0 minus 3. All right, so now with this one right here, then yes, obviously, as far as the sine calculation, I'm not going to worry about final value or anything like that. I'm only going to worry about the final sign. So I call that process. Maybe it's just my own term, but the sine calculation. Numerator, this factor in the numerator is going to give me a negative sign. The one in the denominator is going to give me another negative sign. So negative divided by a negative, it gives me a positive sign as our overall function output. Okay? Positive sign as the output for our rational function for any x values in this interval. X less than 2. Like that. All right. And then, just that. Now let's move on to this one right here. So now I'm going to pick, and so again, so I've purposely shown that thought process, that action earlier, in case we choose a wrong value, wrong in the sense that we pick a value inside of this interval, but it's violate with the domain, pick another one, okay? And so now you already realize how important the domain, being aware about the domain is. So now anywhere between 2 and 3. In my mind, I tend to pick, I'm about to pick, I plan to pick x equals 2.5, okay? Is it going to be any violation with the domain? No, it's not. That's the thought process right there. Okay, so now x equals 2.5 is clearly in between 2 and 3, and then it's not violating with the domain. Here we go. Let's get it work. So now I'm looking at 2.5 minus 2. And then in the denominator, I'm looking at 2.5 minus 3. Okay? And so now as far as the sign calculation, positive sign for the top factor here, but negative sign for the denominator. Positive divided by negative. So now my overall sign for this rational function output in this entire interval has to be negative sign. The negative sign is written in red ink right here to indicate that's the final sign of our rational function in this interval. And now we're ready for the last one right here. I plan to pick x equals 4. But before I really use that into the calculation, let's check if it's violating. Well, x equals 4 is already in the interval here, but we want to make sure it's not violating the domain. The domain is anywhere exclude 3 and 1. 3 and 1. Okay, so in that way, this 4 does not fall into the exception. So we're okay with 4. Okay, we're okay with x equals 4. So now I'm going to go 4 minus 2 as the factor in the numerator, and I'm dividing that by the linear factor. 4 minus 3 in the denominator. So now let's proceed into the sign calculation. So positive sign in the that will come out from the numerator factor right here, and the positive sign again will come out for this bottom one. So now in this entire interval, I know that my function will output a positive value. Okay, and I don't think I need equal sign here. So positive output value will happen for any x value in this interval, x greater than 3. So now we've had all the answer we need right there. Okay, so now let's go back to the other board. All right, so now we just need to look for which interval or which intervals making this rational function eventually simplify to this to be positive. We want to find which interval making this rational function positive, plus sign. And so now which interval or which intervals? This interval is making it positive. This interval is making it positive. So we have two intervals making it positive. Let's record down our result there. I only say record it down. All right. So now I found an interval anywhere between -infinity and 2. And then I found another one. So this is just right from the sign chart right here. Okay. Now this is between 3 and positive infinity. And then we put union between them. But let's not rush. Let's not rushly conclude that, hey, this is our final answer. This is our final answer. Let's find out a little more. We got to make sure each one of these intervals from the Sine chart does not contain the excluded values here. All right, so let's go through them one by one. The first interval from the Sine chart, -2 to 2. Oops, indeed, x equals 1, the value excluded from the domain here is indeed in this interval. In this interval. All right, and so now we got to, so x equals 1 is in this interval. For the other, and that's the only one in this interval. For the other interval, now we move on to the other interval. Well, the interval itself already excluded x equals 3, so we don't have to worry about the other exclusion right there. All right, but now in this one that we found, that in this exclusion that we found, now we have to break this interval. We have to break this interval into two separate other intervals. So now I see that I have to write it as, all right, one interval from between -infinity and 1, excluding 1. And I have another one from 1 and 2, excluding 1. And now we union them. Now we put a union between them. That's how, ladies and gentlemen, that's how we're done. All right, so simply picking the answers from the Sine chart is not is sometimes not the final answer yet. Once you've had all of those answers from the Sine charts, make sure you check carefully to make sure none of the excluded values from the domain here falls into any of those answers from your Sine chart like that. Okay, so for this particular problem, part C of our example, allow me to show the graph to demonstrate the idea right there. Okay, our function here is the x minus 1, the x minus 1 times x minus 2, the rational function, all over x minus 3 times x minus 1. And this function, if we stay away from these excluded x values, we reduce down to that. Let's look at the graph right here. Okay, and now these are the three intervals making the function positive, making this function positive, stays above the x-axis graphically. Okay, let's have a look at that on the graph. All right, so here is my empty graphing space with Desmos, the graphing utility. All right, so this is the graph of our rational function that we recognize through the problem. But then this is the part where we actually need to know, to be compliant with the domain, this function indeed has a hole from our understanding that we've learned. Then this function here indeed has a hole at x equals 1, because see, x equals 1 is excluded from our domain. And that's the idea right here. We have a vertical asymptote at x equals 3 as that result we found. Okay, and so now with this right here, so being positive as a positive interval, see, clearly we have one interval anywhere between -infinity and 1. See, and 1 is clearly excluded from the graph. All right, empty hole right here. So anywhere, so we have one separate interval anywhere between -infinity and 1. This interval doesn't count. This interval between 2 and 3 doesn't count, but interval between 1 and 2. Between 1 and 2, let me now zoom it in right here. See, strictly between 1 and 2, we have our graph still above the x-axis. And that's why these two, from the table, from the Sine chart right here, it's one interval anywhere between -infinity and 2. But see, from our understanding, we have to exclude that point right there. That x value 1. That point x equals 1. And so we now separate that into two separate intervals between -infinity and 1, and then there's 1 and 2, between 1 and 2. And then we have the third interval that is between 3 and positive infinity. All right. Let me put in the vertical asymptote to make the story real clear right there. All right, anywhere between 3 and positive infinity. That's the third interval. So we have one interval, two little interval right here. So one interval, two interval. The second one is very small, and then the third one is this right hand side of that vertical asymptote. All right, and so now we are ready to handle those rational inequalities where the inequality symbol this time does come with the equal sign. Like I said, I primarily focused on those inequalities where the inequality signs did not come with equal signs. And now we're going to spend some time looking at those inequalities where the equal signs come along. Okay, and in my explanation earlier, I see that the kind of inequalities where the inequality symbols come without equal signs happens a lot more in your applications rather than this kind right here. And that's why, when it comes to this, it's only going to be a lot shorter time because all of the big ideas were developed in the earlier part of this lesson already. Okay, and so now we're just going to experiment and we're going to explore what else is being added on top as extra details in order to handle these rational inequalities with the equal sign that comes along. Okay, all right. And so now allow me to show a demo problem. So let's look at x minus 1 divided by x plus 2 times x minus 3. Okay, and we want this to be greater than or equal to 0. And this is what I meant by having equal sign coming along with our inequality symbol right there. We want to solve, okay, we want to solve this inequality, all right, for x. Okay, so before our journey for this kind of inequalities starts, let me just mention, so take all of those details we have learned from the earlier case where the inequality was still without the equal sign. Take all of those steps. The way how I see it now is that now with the equal sign coming along, the extra detail on top is that among the values that we put in on the sign chart, which value among those can we include? That's the extra details. Okay, but it may be a little early right now to mention that. We will explore that as we'll finish through. But all of those ideas all the way through and using the sign chart to answer stays. Okay, all of those ideas stay with us. All right, so now it's already the easy case. Everything is on one side. Okay, all the non-zero things are on one side, successfully factored out as a one rational expression, one rational function. So I'm going to start out by letting a function r of x to equal this x minus 1 all over x plus 2, okay, in parentheses x minus 3 at the denominator. So there we have our rational function. Let's now find a domain. So if we recognize any factor, any common factor that can potentially be cancelled or not, hold it until after you have successfully found out all of the excluded values in the domain right there. Just like how we were doing when it was without the equal sign, just like that, how we've been doing it. Okay, so now I'm going to our first big step is to find the domain first. So the domain here for our function. The domain for our function. So currently, before canceling out common factors or anything like that, I recognize there are two distinct linear factors in my denominator of this current one. And so that means we have to exclude the following. One of them is x equals negative 2. Exclude that out from the domain. And then the other value for x being excluded, x equals 3. We must exclude that. So in other way of saying, in the convenient way of saying, the domain of this rational function is any x value except negative 2 and except 3. We have the domain done. And now once we've done with the domain, let's see if we can potentially cancel away any of the common factors. In this case, there isn't any. So this is our final simplified expression right here. So step 1 here is done just like that, just like how we've been learning it. Step 2 now is also done because it's already in the simplified form. Now we're going to advance to the other board, ready for step 3 and finishing out the problem. All right, so So now as far as the zeros of the numerator, so I'm beginning with step 3 right here. Okay, I only see x minus 1 being the only factor in the numerator, the only and the distinct factor in the numerator, because our simplified or rational expression is here. X minus 1 is still here in the numerator, and that's the only distinct and the only linear factor in our numerator. Okay, and so now finding the zero for that numerator, I'm going to take that only factor, set it equal to 0. This is scratch work at this majority learning of yours, right there, this majority state of your learning already. I'm going to add 1 to both sides to solve for x, and this is scratch work, so x equals 1. I'm going to list that here as one of the zeros in the numerator, and that's the only one. So we're done listing down all the zeros of the numerator. Let's head out for listing down the zeros of the denominator. Okay, so one more time, looking at the final simplified rational function here, I actually see that we have 2 distinct linear factors in my denominator. Okay, so now we're going to find the zeros out of this denominator here. So one distinct linear factor I saw earlier was x plus 2. We're going to set that equal to 0 to solve for x. Okay, and so subtracting 2 from both sides, I have x equals negative 2. So I found one zeros of the denominator, x equals negative 2. That's the 0 in the denominator. Okay, and then I am going to recall that we have another distinct linear factor in the denominator, x minus 3. We're going to set that equal to 0. This is scratch work. I'm adding 3 from both sides of this curtain little equation. All right, and so now I'm going to produce x equals 3 as another 0 of the denominator. Okay, recall again, I'm only looking for zeros of the denominator, so we don't have to particularly worry about domains or anything yet, because we just simply find the zeros of the denominator as the zeros of a polynomial. Okay, so now I have another zeros of the denominator polynomial, x equals 3 here. So we found 2 zeros in the denominator, 1 0 in the numerator. These are all the zeros throughout the whole rational function right here. All right, so now step 3 is completed. Let's advance to step 4 right there. Sine chart. All right, so the sine chart now is ready for action. All right, so let's look at our sine chart on the line of numbers, on the line of real numbers. This time we have 3 values here to be placed on the line of numbers. And so we must break that down into 4 separate intervals here. Okay, so one of them is at negative 2, from the least to the highest right here. The least is on the further left, and then values being placed increasingly to the right hand side. Okay, and so 1 is here and 3 is there. All right, so now we found that there are 4 separate intervals. This first interval is x, is anywhere x less than negative 2. This interval is between negative 2 and 1. See, and right now I'm still excluding including this 0, I'm all excluding those. I'm excluding all of those. I'm treating these as just boundary values between intervals, breaking values between intervals. So this is now x between 1 and 3. Okay, and this is x greater than 3. We're all good with that. We're going to pick values. Okay, so we're going to pick values. So for the first interval, and again, just like how we have seen that in the earlier parts, now anytime we pick a value, we just want to make sure the value we picked does not fall into those values excluded away from the domain. Our domain excluded these 2 values. So make sure any value that we picked to do our test out points right there for sign check, make sure those values we picked have to be aside from these two excluded x values right there. Okay. So now in that way, I am going to pick x equals negative 3. This is completely okay. It passed all the requirements. It's in that interval, and it doesn't fall into any of those values being excluded from the domain. All right, so now here we are. So now I'm going to substitute that into my final simplified expression. So in this still visible part of my other board, but still visible here, allow me to write it down so that I can avoid myself from swinging back and forth between the two boards right there. So x plus 2 is here, and x minus 3 is there. This is our simplified rational expression. Okay, so now substituting x equals negative 3 into this expression over here, I'm looking at, all right, so minus 3 minus 1 in the numerator. And now I'm dividing that by, okay, so here we have, this is a minus 3, this is a plus 2, but it's all about negative 3 substituted in for x. All right, that's how I'm doing it. And so now, in this visible space of my board, a little bit from my other board like this, then the numerator comes out negative, and sign calculation is the only thing we need. Just like that. The denominator here, I have a negative sign for the first factor and another negative sign for the second factor. So it's all negative here. So my overall sign here is negative for this interval. The function, the rational function, this rational function will come out negative output for any x value less than negative 2. That's how it's done for that first interval. All right, so now for the interval between negative 2 and 1, between negative 2 and 1, let's pick a value. I'm going to pick x equals 0. And I just need to make sure, hey, is this value violating with the domain exclusion? It doesn't. It's not violating. So we're good with that value chosen here. All right. So now into the substituting that into the actual function. So now I'm going to substitute 0 for x in each of our factors in the rational expression there. So in the numerator here, it's 0 minus 1. In the denominator for the first factor, 0 plus 2. And then now 0 minus 3. Okay, so now we can start doing the sign calculation. And I see that I need narrower space here. Okay, so I see that I can go, this is negative sign in the denominator. I mean, in the numerator here, it's positive and a negative. So positive sign is here, and a negative sign is here. Okay. And so now our overall sign calculated to be a, so it's negative in the numerator, and in the denominator it's also negative. So negative divided by a negative. So it now turns out positive for the entire interval here. All right. That's the output of this rational function will turn out positive in this entire interval anywhere between negative 2 and 1. Okay, so just like that, now I'm going to pick another value. I'm going to pick a value for this. So how about let's pick x equals 2. Okay, and let's confirm with ourselves. Let's check with ourselves. Is this value okay with the domain? Meaning, is this value violating with any of the values excluded from the domain? No, it's not. All right, so now once again, back in my rational function. These are the factors for my rational functions. It's 2 substituted in for every x values there, for every x value there. So I'm writing it there here. So 2 minus 1, 2 plus 2, and 2 minus 3 right here. Okay, so now I'm looking at, now as far as calculating the signs, I'm looking at, so positive factor on top, positive factor here, but then this last factor is still negative. All right, so calculating out the result right here, we're ending up with an overall negative sign. So if we substitute x equals 2 or any value in this interval into our rational function, the output will turn out negative for x values in this interval. That's what this test is for. All right, so now let's pick the last one. So now I'm going to go with x equals, how about 4? Okay, that's just a choice. Anyone viewing the lesson can choose other values here aside from the one I chose. Just make sure your value that you chose does not violate with the domain requirements. Okay, so now I'm looking at, all right, substituting it in, I'm looking at 4 substituted for every x. Okay, so this is 4 minus 1 here, 4 plus 2 here, and 4 minus 3 here. And now you have seen that enough. I'm going to just get directly into the final sign calculated here. That's going to give me a total sign, an overall sign being positive. That's why I wrote it in red ink. All right, positive. Okay, so now, I don't think I need this anymore. The question from the beginning wants us to find those values of x, or those intervals of x that makes the left-hand side or this rational function to be greater than or equal to 0, greater than or equal to 0. But let's primarily focus on the greater than 0 first, just like how we've been doing the earlier kinds of problem where the inequality was still a strict inequality. So for now, let's not worry about the equal sign yet, okay? Let's not worry about the equal sign. So more primarily, which intervals from our sign chart make the left side here positive, okay? Because we want that positive. So now, for positive, this interval is positive. This interval between -2 and 1 is positive. This interval is also positive between 3 and positive infinity. Okay, we have 2 positive intervals. Let's write it down. Let's document it down. So I have found 2 intervals. One of them between -2 and 1. For now, let's put it all parentheses, open interval for now. And then the other one here, the other one is 3, between 3 and positive infinity. And we put a union, just like that. So if this was and of course, we're considering through with all of the domain check right here, and we're all good. We are free from the domain worry right there, from the domain the requirement. So we're all good with these 2 intervals. So there's no need to break them down into sub-intervals among any of these intervals here. But now, if this was the problem where it was strictly greater than 0, then we're done right here. We would be done right here. But now for this problem, since we want the left-hand side greater than, yes, these making it greater than, but also equal as well as equal, greater than or equal. So that means now it's all ones we've done with all of these ones we've done and picked all of the intervals that satisfy the inequality first. Okay, satisfy the strict inequality first. Now to handle the equal sign, we just simply need to look at any of these endpoints right here, the -2, the 1, the 3 right here. Well, it will never be brackets for the infinity, so we never have to worry about the infinity. But we have these definite endpoints of the interval at the -2, at the 1, at the 3 right here. Which one of those can be, see, that I only put in this question when it's the inequality with the equal sign that comes along. So which one of these, -2 or 1 or 3, can have brackets? Let me repeat. It's all because this inequality we're handling now has the equal sign coming along. And now nothing wrong with this. Suppose we already collected all of our intervals correctly from the table, from the sign chart table right here. Now the next question, just the last extra question, which one of these can be included? The -2 or the 1 or the 3? Which one of these can be included? It could be 1 or 2 or all 3 of them, or it could be none of them to be included. That's the question. Which one of these can be included? All right, so we'll go through them one by one right here. Keep in mind again, the infinity will never be included. It's because it's infinity. It's the way how we do things in math. We don't include infinity, okay? Because it's not even a real number. It's not even an actual number to include. But now, in order to decide, we need to go side by side and really side by side with the domain listed here. Hey, the domain is excluding these values, 3 and -2. 3 and -2, and those are here. So these guys should never be brackets. So they're good where they are. They're good where they are with parentheses. So these 2 are good. This guy, is that violating the domain? No. If we put brackets there, is it violating? If we're including x equals 1 Is it violating the domain? No. And as a matter of fact, if we put x equals 1, x equals 1 is the 0 of the numerator, so it gives me a 0 divided by anything else non-zero. So we do have equals 0 here if x equals 1. That's how I decided. So it's all about once we've successfully picked all of our intervals that answer the question, the primary question is that strict inequality. We put those, we list down those intervals from the table, from the sign chart table, and we're gonna just simply gonna compare with the domain right here. Any of those any of the endpoints that free from the domain requirements right here, then we can use brackets on them. So 1 is free from the domain restriction. The domain restriction is only indicating that we need to be anywhere except -2 and 3. 1 is not any one of these. Okay, so we can include 1 just fine to make this left side equal 0. Ladies and gentlemen, now your answer is done. We're done with that answer, with that work. All right, so this is the end of this demo problem right here. Before I'm heading into some actual the example problems, let's have a look at the graph of this problem right here. Our rational function is x minus 1 over x plus 2 times x minus 3 in parentheses. Okay, and then let's look at the graph and see if it's consistent. We want to be greater than, we want the part of the graph to be greater than or even hits the x-axis. That's what equals 0 means. So which interval allows the graph to be above or as low as right on the x-axis? Okay, let's find out. All right, so now this is our empty graphing space with decimals, the graphing utility. All right, and this is now the graph for our function x minus 1 all over x plus 2 times x minus 3 in the denominator. All right, so this is the graph. And in our experience learning at this point, we know that this function has 2 vertical asymptotes, but that's not the directly irrelevant information. But I can just put in the vertical asymptotes to assist our view of the graph right here. So 1 at x equals -2 and 1 at x equals 3. And that is the reason why we're excluding our x equals 3 and x equals -2 from our function. But now x equals 1, right here at x equals 1, we do have a solid point right here. Okay, so now allow me to put in that point right here. Okay, x equals 1. All right, so right there the y value equals 1. So now let's check for consistency right here. We're looking for the intervals causing our functions, our rational function here, to be greater than or equal to 0. So above the x-axis or hitting down to as low as y equals 0. So now see this interval anywhere between -2 up to +1. See this one right here the graph legally crosses through the x-axis. So now anywhere between -1 or anywhere between -2 and up to 1. Okay, and that's this interval right here explained for that interval. All right, and then the other interval between 3 and +infinity. You're seeing that on the graph right there, would you? Okay, from where that the vertical asymptote at x equals 3 to the right hand side. All right, this is the interval the graph is completely above and will never hit the x-axis. The graph is completely above, positive, anywhere between 3 and +infinity. All right, and that's how we're doing this demo problem, and the graph explains that. All right, so at this point we are ready for some actual example right here. And so to continue from the earlier example number, let's now call that example 2 right here. All right. Example 2. All right, so now let's resolve the following. Rational inequality for x. All right, So now part A of the example, let's look at about x minus 3 times x minus 2, and we're dividing that by x minus 1. This is the denominator, and we want our left-hand side here to be less than or equal 0. So now there's equal sign that comes along in our inequality. Okay, so now, but all the steps comes along, all the steps that we've learned prior to this kind of inequality. So the whole example 2 now is designated for that class of rational inequality where equal signs come along in each of our inequalities. Okay, and so now, just like that, the easier case, we're here already in a sense that all non-zero terms are on one side and the opposite term is 0, and we further got everything factored out completely. That's a good thing. In case any of our polynomials here was not factored, spend a little time factor it out before we get started. That's just a high recommendation. Okay, so let R of x be the x minus 3 times the x minus 2 divided by x minus 1. This is our formal rational function. Okay, and so from this rational function we are going to, as usual, find the domain. Okay, identify the domain of this function. So the domain here at this point when you're learning this, assuming you are already mature in working with rational function, the domain of this rational function is just simply any x values except x equals 1. Okay, all right, so now we are ready for that. Next step, simplifying possibly, okay, possibly simplifying any of these common factors, but we recognize there is none. There isn't any common factor to be recognized. So this is our final rational function right there, the simplified version. All right, so now I'm going to navigate to the other board and let's get our work ready. And so now we can use this space here of the board to construct a Sine chart and solve our problem. Okay, so in this little visible corner of my other board, allow me to rewrite the function R of x right here. So R of x, okay, and that equals, so here I have x minus 3 in parentheses times x minus 2, and then that's divided by the x minus 1. Okay, that's the rational function. So now to find, we are at that third step where we need to find all the zeros from the numerator and from the denominator. Okay, so now the numerator has two distinct linear factors. So one of them is going to give me, so I'm going to set the first one, x minus 3, to equal 0. All right, and that's solving for that. For x, from this equation, I'm looking at x equals 3. I found 1, 0 of the numerator. And then we're doing it again for the other factor. Okay, x minus 2 is set equal to 0. That's the next distinct linear factor in our rational function. Okay, in our numerator of the rational function. So now adding 2 to both sides, I'm looking at x equals 2. I have found another 0 of my numerator, and that's all the zeros of my numerator. Let's now look at the denominator, and this is the distinct and the only one linear factor in our denominator. All right, so now I'm going to simply set that x minus 1 equals 0, that denominator, adding 1 to both sides, that's going to solve for x right here, and x now equals 1. Okay, so now this is a 0, but of the denominator, zeros of the denominator. Okay, so let's get to work. So now we found all zeros from the numerator and from the denominator. All right, so now let's get to work. Here comes the Sine chart. By the way, at this point, it's the end of our third step right here. Okay, we have found all zeros from the numerator and the zeros from the denominator together as a comprehensive list. So now I'm going to construct the Sine chart. All right, so as far as the Sine chart, here comes my line of real values. Okay, so we have we have 3 separate zeros from the numerator and from the denominator. So increasingly from the left to the right, 1 has to be here, 2 is here, and 3 is here. Okay, and now we can create columns. And at this point right here, we don't need to worry about which one of these has to be included. That's not what to worry at this point yet. So on the Sine chart, we strictly look at things between these intervals, right? Inside of each of these intervals. That means between these consecutive or adjacent values like that. All right. So the first interval to come, we're looking at those x values being less than 1. Less than 1. Less than 1. Okay. And so now I'm going to pick x equals 0, for example. And you can try a different value. X equals 0. Okay. Into my, and again, just to get into that good habit, anytime I pick a value, I got to make sure the value picked here, the value selected here is free from the domain requirement. Is okay from the is compliant with the domain requirements. It is. Okay. So now I'm looking at substituting this into my current rational expression. X minus 3 times x minus 2 all over x minus 1. Okay. And so now I'm looking at, all right, producing these pairs of parentheses. All right, so 0 substituted in for every x. So 0 minus 3, 0 minus 2, and 0 minus 1. All right, so now as far as calculating the overall sign, this is what I see here. It's a negative sign for the first factor. It's also the negative sign for the second factor in the numerator and divided by the negative sign in the denominator. All right, so my overall sign for this interval has to be a negative sign overall, because on top it's positive, negative times negative is positive, but divided by a negative, we're looking at a negative sign overall. All right. And so now we're going to pick a value in this interval where x is between 1 and 2. Between 1 and 2. So we can pick x equals 1.5. You can pick a different value. Okay? And let's check. But let's make sure that we check to ensure that the value we've selected here is compliant with the domain requirements. The domain says we have to pick any x values. We have to work with any x values aside from x equals 1. This is already aside from x equals 1, not x equals 1. We're good. So now into our rational function. All right, I'm going to substitute 1.5 for each x value. All right, and so now I'm subtracting 3, subtracting 2, subtracting 1 right here. Okay. So as far as calculating the signs, the first factor here is going to give me a negative sign. The second one is also negative sign. But the third one in the denominator gives me a positive sign. All right, that's how I'm proceeding into my sign calculation. So now at the end, the rational function we're working with is having a positive sign, an overall positive sign in the entire interval between 1 and 2. That's what the red positive sign is for. All right, so now we're done with that interval for x values between 1 and 2. Let's move on to the next one right here. So this interval is designated for those x values between 2 and 3. I'm going to pick, how about x equals 2.5. Okay, you can pick a different value, but let's all make sure that the value we picked is compliant with the domain's requirements. Okay, the requirements of the domain says x must be other than 1 anywhere but except x equals 1. This value is clearly not, so no worries. Okay, so now back into the function again. All right, so 2.5 substituted for every x. Okay, so I wrote it in first because I'm all in red ink mode. So minus 3, minus 2, and minus 1. Okay, so let's now calculate the sign here. This first one here, this first factor is going to give me a negative sign. This one here now will give me a positive sign. And the bottom one here is giving me a positive sign again. So that means as an overall sign, after doing this calculation, negative times positive gives me a negative, but divide by a positive, so it's all going to be a negative sign as the overall final answer. All right, we see one by one we got solid method to finish each interval, each of the intervals here in terms of finding the overall final sign. And the whole method here is called the sign check or the sign chart method. Okay, we use a sign chart to check for the sign. All right, so some other professors also call this the sign check method right here. There's so many different ways of calling it. X greater than 3 is this interval. Okay, and now we can pick x equals, I can pick x equals 4, but that's just what I picked. You can pick a different value as long as it's satisfying that requirements greater than 3 and also compliant with the domain requirements. X equals 4 here, is it aside from x equals 1? Yes, it is, right? It's not violating with the exclusion of x equals 1. So now we're good to go with that. So now substitute it in for each x value. Now I'm going to subtract 3, I'm going to subtract 2 in the numerator, and I'm subtracting 1 in the denominator. So as far as calculating the sign, I'm looking at positive sign for the first factor here, another positive sign here, and then another positive sign in the denominator. All right, so now my overall sign of this rational function in this interval has to be a positive sign. All right, positive sign. Has to be positive sign. Okay, so we're good with for now. This is the end of the sign chart, the sign check table right here. Let's get back on the other board and try to precisely answer our question. So the inequality is asking us, the problem is asking us to find the interval or the intervals of x that makes this rational function primarily negative below 0. Primarily, I highlight that word. I want to find the interval or the intervals primarily making this rational function negative. So we do it just as usual. We're doing it just like how we were doing in example 1 and the earlier kind of problem. So primarily less than 1. I mean less than 0 right here. Let's look it up from the sign chart. The sign chart says this first interval where x is less than 1 is negative. This third interval where x is between 2 and 3 is another negative 1. We have two intervals from the sign charts. Let's put them together. So now I'm looking at anywhere between minus infinity and 1. Okay, and for now, let's just leave them all with parentheses, open intervals. And then the next one I found from the sign chart is 2 and 3, between 2 and 3. And for now, again, let's put them all with parentheses, and then union between them. So if this was a problem in example 1, we're done right here, because we're strictly looking for just strictly less than 0. But now in this problem here, and since we're in this next subclass of rational inequalities where there is equal sign involved, we just want to see that, hey, among these endpoints, the 1, the 2, or the 3, which ones among these can be included in our intervals? All right, which one among these can be included in our intervals? Okay, so let's find out. Of course, the negative infinity here can never be included. It's the way how we run math, okay? So parentheses here. This 1 right here, can it be included? The answer is no, it can't, because the domain is saying that we have to exclude 1 always. So this interval now is good, all good. That interval now is all good. And then this exclusion right here does not fall in, is not contained in any of our inequalities, so we're completely good. All right, I should have mentioned that in the demo problem as well, but it's been completely free with that. Okay, so, but the next interval here, the next interval, can I include 2? Can I include 2? X equals 2. So x equals 2. Okay, can I include x equals 2? The x equals 2 is just simply the free from this domain requirement. So yes, why not? Because when x equals 2, x minus 2 will equal 0, making the entire rational function on the left-hand side equal 0. So x equals 2 can be included. Now I'm going to adjust this and this left end of the interval to close interval brackets there. See, it's all about, so when we first writing it down, it's all parentheses, and then we're going to redecide which one among these endpoints can be changed to brackets for including, which one among these can be included, and which ones must stay excluded permanently. All right, and so what about the 3? Okay, the 3 here, first thing I see, the 3 is not is free from this domain requirements. It's free from that domain worry right there. So we're good to go, because the domain says we can take any value, right? We can take any value except 1. So now we can take 3. And besides, the inequality is asking for equals 0. So that 3 right here, and see, like I said, equals 0 in the inequality, like how I was introducing that earlier. It's all about, so now which one of these can be equal to 0? Which one of these can be included, I mean. Okay, which one of these domain can be included? Because including these will make it equal to 0. So we cannot take this because it violates the domain requirements. We cannot take infinity, we leave that parentheses. But now this, yes, we take both of these. So now it's brackets here, closed interval here completely, and open interval here. That's the end of our work, and that's our final answer. That's our final answer. All right, so for this problem, allow me again to swing over to the graph and show the graphical illustration to really go side by side and let the graph explain our understanding. So we have 2 intervals here. One of them is the open interval completely. The other one is the closed interval, okay? All right, so now in the empty graphing space with my Desmos graphing utility right here, let's look at the graph for our function R of x. So our rational function R of x, that equals x minus 2 times x minus 3 all over x minus 1 is here. This is the graph. And then from our understanding that we have already learned, we have a vertical asymptote for this graph right here. Okay, and I can put it in. So we have a vertical asymptote at x equals 1, even though at the very beginning of the lecture I said it's not important that we know whether or not we have a vertical asymptote for this graph. But now here you can see that the graph is crossing with the x-axis as 2 values right here, x equals 2 and x equals 3. Okay. So with this graph right here, now let me put in those intersection points. All right, so we have one intersection point here, and we have another one at 3. Okay, so now as far as the interval, so according to the result shown in the graph right here, okay, let me put it in some view that's making it easy for us to view. So we want the interval where the graph is below the x-axis. We want the interval where the graph is primarily below the x-axis, okay? And so now, in that way, we saw that we have one interval anywhere between negative infinity and 1. That's why I put in this vertical asymptote here as the line that splits the boundary for this is right at 1 right here. So anywhere between negative infinity and 1. The graph, the part of the graph in this interval to the left of x equals 1 is completely below the x-axis, as we can all see it here. All right, and then other than that, we see another interval. So it looks like between 2 and 3, there's another interval where the graph sinks below the x-axis, and that's shown here. All right, and then anywhere else outside from those 2 intervals, the graph stays above the x-axis. Let me zoom it out in some extreme far zoom so that we can have a better understanding of the shape of the graph. All right, and now back to the zoom mode right here. So now The reason I can legally put in these solid points is simply because it agrees. See, the graph does have defined value and it crosses with the x-axis, right, at x equals 2 and x equals 3. As a matter of fact, that agrees with what we have found at the zeros of the numerator. Okay? These are x equals 3 and x equals 2. So at x equals 3, we have the graph going right through the x-axis. And at x equals 3, we have the graph, again, goes right through the x-axis. All right. And so now in that way, that confirms our understanding. We have one interval anywhere between negative infinity and 1, and we have another interval anywhere from 2 to 3. That is just directly consistent with this result that we have concluded on the board here. All right. And now we are ready for one more problem in example 2 here. Okay, so let's look at part B of the example. The inequality we're looking at here is about x plus 2 times x minus 2 all square, and we're dividing this by x minus 2 times x minus 3, and we want this to be greater than or equal 0. We want that to be greater than or equal to 0. Okay, and so now, once again, before solving this, we're going to let we're going to let a function r of x to be defined as this left-hand side expression here. So x plus 2 times x minus 2 all square and divided by x minus 2 times x minus 3. Okay, we already recognize there are some common factor that can potentially be canceled or simplified away, but we're not doing that yet. Okay, so right from here, once we have recognized successfully our rational function, in a sense that, see, everything is put on the left-hand side, only leaving a 0 on the opposite side, and things are all completely in factor form. Okay, so now I'm going to go ahead and find the domain first. We got to find the domain before we do any simplification work. All right, so now domain for this particular rational function that I recognized is going to be any x value except 2 and any x value except 3. So the domain excludes out these two x values here on our list. Okay, x cannot be equal to and x cannot equal to 3. That's how it is. And now we can start canceling canceling common factor out. So I recognize there's this common factor being x minus 2. Okay, I cancel that, and then this cancel this out. Here leaves behind one factor x minus 2 left behind in the numerator. So my final expression here, my final rational function here in the next step, r of x here is simplified down to x plus 2 times x minus 2, and we're dividing that by x minus 3. All right, and that's our simplified rational function. And now we're going to use that simplified version for the next steps. All right. And now I'm ready to head into step 3 to find all zeros of the numerator and the denominator. And then at this point, since you have seen the idea of using the sign chart often enough, allow me to start picking up the pace on those. Okay. So now, first of all, as far as listing down all the zeros of numerator and denominator, numerator has these two distinct factors. So x plus 2, first one, I'm going to set it equal to 0, subtracting 2 from both sides. That leaves me x equals negative 2. I have found one zero of the numerator. X equals negative 2. All right. And then the next one, x minus 2 equals 0. That next factor right here, I'm going to set that equal to 0. Adding 2 to both sides will solve my x value. So x equals positive 2. So I have found another 0 in my numerator. All right. And now I'm moving on to my denominator. Okay. So x minus 3 is the distinct factor and the only factor I found in the denominator. So I'm going to add 3 from both sides, setting that equal to 0, and add 3 from both sides. Okay, I'm looking at x equals 3. This is the only 0 in my denominator, x equals 3. All right, and so now we are ready for putting all of these three values, these three zeros, from the simplified rational function to the sign chart right here. Okay. All right, so here comes the sign charts. All right, so I'm going to place all these three values here, -2 here first, and now I'm looking at this 2 and this 2, and then there's 3. Okay, and so this first interval is indicating anywhere of the x values less than -2. And this is for any x values between -2 and 2, and this is for any x value between 2 and 3, and this is for any x value greater than 3. All right. Okay, so now I'm gonna pick, and again, you gotta always stay compliant with the domain requirements. So now picking a value less than -2, we can go with x equals -3. Check yourself this question. Is this value compliant with the domain requirements? Yes, it is. So that means now into my rational function that's still visible here on this from this other board right there. So I'm looking at all right, -3 substituted in for every x. All right, and now it's +2, -2 here, and -3 there. So that means we're looking at that first factor here being negative. This is even further negative, and this bottom one is negative again. That's calculating the sign. So my overall sign here is a negative sign. All right. This next interval. So I'm going to pick, so between -2 and 2, I can pick x equals 0. Okay, and you can pick other values as long as our value is compliant with the domain requirements, which is, yes, it is compliant with the domain requirements in this selected value, for this selected value. So now I'm going to go, once again, calculate the sign behavior. Substitute 0 into every x value there. This is +2, this is -2, this is a -3. So it's giving me positive for the first factor, and then negative for the second one, and then negative for the bottom one. All right, so I'm looking at here an overall, so it's negative divided by negative. It's positive multiplied with another positive there, it's positive. That's the overall sign of it in that interval. All right, so now with this one right here, x between 2 and 3. So now I'm going to pick, how about x equals a 2.5? Okay, and so So 2.5 is going to be substituted into my x value in the rational function. Okay, so now 2.5 plus 2, okay, 2.5 minus 2, and 2.5 minus 3. All right. So now I'm looking at, so at this point, I'm going to pick up the pace right here. That's positive, okay, and that here is negative. So my overall sign here in this is negative. Okay, because once again, this is positive sign right here. This is positive, and this is negative. That's what my arrow is indicating. All right, and then let's look at the last one right here. Yes, I'm going to pick, how about x equals 4? And let's check again for the compliance with the requirements of the domain right here. So yes, it is compliant with the domain requirements. So now I'm going to look at substituting it in. 4, 4, 4. This is plus 2, minus 2, minus 3. Okay, so the first factor here is positive. The next one here is positive. The last one here in the bottom is also positive. So now my overall sign is positive, that big giant plus sign right there. So that's how we complete the sign chart. All right, so now let's move on to the other board to answer our final question right there. All right, so here primarily I use starting with into that kind of inequality where equal sign comes along. I use that term primarily. So the bigger thing is being positive. Okay, so primarily for the intervals that make the left hand side positive, we're looking at those intervals anywhere between -2 and 2, and right from the start, just write it down with parentheses. Okay, and then we're gonna redecide who among these endpoints can be included because of that zero. Because of that equal sign, like that equal sign. So first of all, between -2 and 2. Another one is between 3 and positive infinity. And I put unions between them. All right, so now, but this is not the final answer here. If this problem was a problem from our example 1 right there, then we would stop right here. And of course, this is already after checking. After checking to ensure that none of our excluded values falls into these selected intervals. Right there. So we're all good with that side right there. So it's compliant. These intervals are all good and properly compliant with the domains right there. Okay, but now we want to find out further which one among these endpoints is that the -2, the 2, or the 3, or all of them, or only one of them or two of them. Which one there, or which ones there can be included in their intervals? Let's go from one by one. -2, can this be included? Why not? Because it does not violate the domain requirements. It does not violate any of the domain requirements at all. And as a matter of fact, substituting x equals -2 into the function here originally, okay, we had x plus 2, so -2 plus 2, making it 0. These are all non-zero, so the whole function here will turn out equals 0, simply because x equals -2. So now I can change that. Now I will change this to brackets. All right. And then the next one right here, can I change this? Can I include x equals 2? But right here, when x equals 2, it violates this domain requirements. So, nope, we have to leave this as open parentheses. All right, and now we move on to the third one here, x equals 3. We have to check, does this violate our domain's requirements? Okay, the domain requirements is here, and yes, x equals 3 violates the domain requirements, so this has to stay parentheses. And of course, infinity will always be with parentheses. So now we know that we are done. It's finding the answer, all the intervals that answer our inequality right here, greater than or equal to 0. That rational function, greater than or equal to 0. All right. And again, before I'm completely leaving this example over here, allow me to show the graph of this function so that we have a clear picture and see how the graph agrees with this particular answer over here. We want to be above 0. We want to find out the intervals of the graph that's above 0. Okay, and where will it hit the line x equals y equals 0 right there, the x-axis. All right. All right, so now on our empty graphing space with my Desmos utility, my Desmos graphing utility, this is the graph for our rational function. All right, and let me show the complete full view of that. All right, so this rational function, in our understanding, we knew it had a vertical asymptote at x equals 3, okay, from our understanding. And this is good to know, but as I said, it's not required to learn this material before we've learned about rational inequality. So if you know this, that's good. If you don't, that's okay. But this function, this graph, will have a hole at x equals 2. Okay. So there's the hole at x equals 2, and And then when you learn my video lesson about what a hole of a rational function is, you will have a clear understanding of why we have a hole there. But a hole here really means we just cannot see. This is agreeing with the domain right here. The domain exclude x equals 3 and exclude x equals 2. But now we're looking for the interval of the graph, the interval of the graph where the graph is positive above the x-axis. The x-axis is here, above the x-axis. So it looks like this interval between anywhere from -2 to less than 2 right here. This interval is positive. And then this other interval anywhere between 3 and positive infinity is another interval being where the graph is above the x-axis. And I can put in that solid point right here to make the interval real clear. And this is what explains that we have brackets right here and open parentheses here. Since we're not including, we can't include x equals 2. And then anywhere between 3 and positive infinity. And that's why we have parentheses on the 3 and then on the infinity. And that's why it's and that's how it's consistent with this answer that we have addressed here. All right.